Lines and curves in space, Part 1. A function of the form r of t equals the vector x of t, y of t, z of t is a set of three parametric equations that describe a curve in space. It is a vector-valued function where each component x, y, z varies with respect to the independent variable t. Note that the point x of t, y of t, z of t on a parametric curve is the head of the position vector r equals x of t, y of t, z of t. Here I'm having you look at the e-book found in my math lab. I'm going to click on the play button so that you can see that as time increases, the object moves along the parameterized curve. Each point on the curve is represented by a vector. So to reiterate, the vector-valued function gives the position of an object for a particular time. Let's examine this parameterized curve. R of t equals cosine of ti plus sine tj plus t times k. To visualize this curve, first focus on the x-y components. What do you see as you look down? That is, as you project the curve onto the xy plane. The first two components tell us that as we look down, we see the object traveling counterclockwise around a circle of radius 1. The third component tells us that as the object travels in a circle, it is also increasing in vertical height. In the e-book, they will show us the helix for time going between 0 and 2 pi. So as time increases, my object is going around, but it also increases in height, so that when it gets back to the x-axis, it's above the x-axis. It's a little more fun to see it done with a time period of 4 pi. Okay, so let's look at another parameterization. This parameterization, notice that the first two components tell us that as we look down, we see the object traveling counterclockwise in a circle of radius 1. That's the same as what we had before. But now let's look at the z component. It has amplitude 0.4 and period of 2 pi divided by the coefficient of 2, so it has a period of pi. So the z component rises to 0.4 and falls to negative 0.4, and it does this twice in the time given. Going back to the e-book and hitting play, I can see the curve being played out. Want to see that again? Let's do that one more time. So in a time of 2 pi, it goes up and down twice and around as well. And that's our roller coaster curve. All right, our last parameterization for this part 1. This one is fairly complex, and don't be surprised if you get confused. I'm going to try to see if I can help you understand what we're looking at. To get a handle on this curve, we will compare it to the roller coaster curve we just examined. First, look at the z component of each parameterization. They're very similar, but what is the difference that you see? The amplitude is the same. It goes up to 0.4 and down to 0.4. But the z component of the mystery curve rises and falls 20 times rather than 2. Looking at the x and y components, it appears the object of the mystery curve, like the roller coaster curve, is traveling in a circle of sorts, but something else is going on. First, let's look at the new x component of the mystery curve. The x component now has a varying amplitude with 20 oscillations. And next, look at the new y component. The y component also has varying amplitude with 20 oscillations. Okay, do you think you can wrap your mind around that? Let's go back to the ebook. Okay, are you ready? So the z is going up and down, and also looking down there seems to be a going around movement, but the x and y amplitudes are going up and down. So let's just look just at the position for time t. So this just gives the position for time t. That's not very helpful, is it? Let's do it again, but this time let's click on the thing that says show the curve. So let's this time show the curve, and let's go back and hit play. There we go. So that's about pi over 2. We're getting close to pi. Pi is right there. And 3 pi over 2 and 2 pi. And there we go. Bet you couldn't have guessed that. Could you? I'll be impressed if you can. So our mystery curve is the slinky. And this is the end of part 1. In part 2, we're going to do lines, parameterizations of lines. That'll be a little bit easier for us to visualize. Okay, take care and I'll see you then.